Hello there, this is Alfred Posamentier. I'm currently Dean of the School of Education at Mercy College in New York, and I spent the previous 40 years as a member of the faculty at the City College of New York, at City University of New York, the last 25 as Associate Dean and then Dean, actually the last 10 years as Dean, and my area of academic interest is mathematics and mathematics education. For years, I've been consumed by trying to make the teaching of mathematics interesting and exciting. And in 2002, I had a very interesting event in my life. I was urged to write an op-ed about the palindromic number 2002, and the New York Times published it half page on the 2nd of January 2002, and I simply talked about palindromic numbers and how you can generate them in mathematics and so on. And of course, I use that as a podium for talking about mathematics, making mathematics interesting. One of the things that I've found over the years is whenever I get into a social event and I tell people that my field is mathematics, the first thing I hear from about 90-some-odd% is, oh, I was always terrible in mathematics. No one is proud to be bad in any other subject in their school years as they are about mathematics. Mathematics takes the cake all the time. It's almost as though it's a badge of honor to have been lousy in mathematics in school. Well, following this op-ed I did in the New York Times, I must have gotten about 400 emails, and 2 of them came from publishers asking me if I could write a book that would be of interest to the general audience. Well, I've done that now for the past 9 years, on an average about 1 a year, on topics that I thought would be of interest to the general audience. Now, of course, when I speak of the general audience, I'm speaking of people who are somewhat, have some possibility of being interested in mathematics, or some who are in fields where they have studied some mathematics, but never from a recreational point of view or from a human interest point of view. Some of the books I've done, the first one was on Math Charmers, which was a book about all kinds of different topics, very, very brief little vignettes that could be used to turn people on to math. Publisher felt that worked well, so they suggested, can you write something else? I said, what else is there about mathematics that would be of interest? I thought about it. I said, well, everybody talks about pi, 3.14, and then now we have a Pi Day, 314, which happens to be Einstein's birthday as well. And so I decided I'd write a book on pi, and it's called Pi, Biography of the World's Most Mysterious Number. Well, that worked, and they said, well, do another one. I said, well, okay. Did one on the fabulous Fibonacci numbers. Magnificent set of numbers that just permeates everything. We'll talk about that a little bit today. But what I'd like to do here is, not knowing who my audience really is, just to kind of ease you in and show you some of the truly outstanding, amazing things in mathematics. By the way, I did write a book called Mathematical Amazements and Surprises, which also is loaded with these gee whiz kinds of things. So let's go for a little path through some of these things. And if we take a look at this a set of numbers here, you'll notice we have a set of numbers, look like just any numbers, where each one is squared, and we add them, subtract a few, and we come up with 0. Well, there's nothing spectacular about that. But now watch what happens if we were to chop off the 100,000th place on each of these numbers. Look what happens. The sum still remains 0. That's amazing. Not only that, but we take those numbers again and again chop off the first digit. The sum is still 0. And if we continue this process, chopping off the leftmost digit, we find that the sum continues to remain to be 0. This is truly an amazing aspect of arithmetic or number properties. I guess you might say it's a quirk of the decimal number system. And it goes down to 2-digit numbers, and then, of course, as you would have expected, with the last single digits, we once again have a sum of 0. Now, just to know, we start off with just a set of numbers, and by chopping off the leftmost digit, we kept on getting the same sum. you're probably wondering, well, what happens if we chop off the units digit each time? Well, you guessed it. The same thing is going to happen. We have a set of numbers here. We chop off the rightmost digit, the units digit, each time, and you'll notice each time the set is the sum and difference here is always going to remain to be 0. Quite an amazing thing. And here we have it. Okay, now we look at this again, and you say, well, that was pretty neat, but it looks like it was a fix. Well, supposing this time we chop off on the right and the left simultaneously, notice what happens here. Again, the sum is always 0. This is just one little thing. Now, a lot of people have heard about the number 666. It comes up all over. Certainly in biblical terms, it's the number of the beast and a number of other sort of non-mathematical applications. But let's take a look at what that number really looks like. Well, if we were to write the number 666 in Roman numerals, which all of you I'm sure can do, look what happens. We have all the numerals, in all the Roman numerals, less than 1,000, used in descending order. And for those of you that may not remember what the D and the C represent, here you have it. So you have the number 666 uses all the Roman numerals less than 1,000 in descending order. Let's take another look here. Suppose we take the first 36 natural numbers, 1, 2, 3, 4, 5, all the way up to 36. Guess what? The sum is 666. Gets you to start wondering about this number. Well, let's take it a step further. Supposing we take the sum of the squares of the first 7 prime numbers. Well, once again, you might think this is rigged, and it probably is, but it works. We didn't fix anything. The first 7 prime numbers, 2, 3, 5, 7, 11, 13, 17, each one squared, sum them up, and you get again 666. Well, we're not done yet. The sum of the numbers 666 is equal to the sum of the digits of its prime factors. So take a look at the number 666, which we're going to break up into its prime factors, namely 2 times 3 times 3 times 37. And look what happens if we add up those digits. We get 6 plus 6 plus 6, or a form of 666. And if you sum 2 consecutive palindromic numbers, now these are 2 consecutive palindromic prime numbers. And if you take those two, 313 plus 353, once again, bingo, 666. There are many strange occurrences of the number 666 when we add plus signs to the sequence of numbers. Take the numbers, the natural numbers up to 9, 1, 2, 3, all the way up to 9. And we're going to stick plus signs in this thing to make it come out to 666. For example, here you have 1 plus 2 plus 3 plus 4, then 5, 6, 7 is a number, plus 8, 9 is another, 89 is another number, you get 666. Or we can do it this way. 123 plus 456 plus 78 plus 9, again, 666. Consider the sequence in reverse. This time 9, 8, 7, 6, 5, 4, 3, 2, 1. Again, we can create 66 as follows by taking those numbers in their order, just locating their, plus signs appropriately, and we get, again, 666. Not only that, if you take the value of pi, which we now have to well over 1 trillion places. Now, you're probably wondering, why would anyone bother to go through this hassle of getting pi to over 1 trillion places? The reason is not that we need the numbers or that we need such exactness, but it's used to check computers to see how fast and how accurate new computers can be. And so that's why we try to get pi to more and more places. But here we take pi to the first 144 places, and if we add that up, those numbers, those single-digit numbers, once again, 666. Now, you'll see in a moment how we're going to tie 66 again in, but before we do that, I need to just quickly introduce you to the most ubiquitous numbers that probably exist in our number system. They're known as the Fibonacci numbers, named after Leonardo Pisano, or Leonardo of Pisa. And we'll give you just a quick biography. Now, Leonardo wasn't called Fibonacci in his time. He was son of a family of Bonacci, and the Felice Bonacci, or it evolved to Fibonacci. It's believed that Edouard Lucas, a French mathematician, was the one who coined him as Fibonacci. Now, he was born, we think, as best we can tell, he lived from 1175 to 1250. But his fame came, in today's world, from a book called Libera Baci, or perhaps Book of Calculations, which he published in the year 1202. 1202. A second edition of that book, published in 1228, I believe is in the Science Museum in the city of Florence, Italy. But the book, remember, there was no printing press. This was a handwritten book with many chapters dealing with problems of bartering, land measurement, things that were of interest to people from the point of view of mathematics in his time. The amazing thing that no one thinks about, that I can tell, at least in everyday life, is that what we call Hindu Arabic numerals, the numerals that we use in everyday life, stem from his introducing them into the Western world in the book Libera Baci. His father was a customs agent in northern Africa, and he spent a lot of time in the Arabic world and worked with mathematicians and was amazed at the numerals that they were using, which they got from India. Hence, we call them Hindu, from India, Arabic numerals. And these numerals, which we use today, were used throughout his book. And in that book, in chapter 12, he has a problem about the regeneration of rabbits. It is that one problem that generated the Fibonacci numbers that we know today. The first sentence, the very first sentence in his book, he talks, the Indian, of course not in English, the Indian figures are, and then he says, he puts these numerals out there, 987654321, and he says, these 9 figures with the sign of a 0, which the Arabs call Zephyr, any number whatsoever is written and is demonstrated below. And he goes on to showing what these numerals are, and he says he's going to use them throughout the book. Now, what's of particular interest here is, this is my interpretation, it could be wrong, why did he write those numerals in a reverse order? Probably because that's the way he saw them. The Arabs write from right to left. And so that's probably the way he saw them, and that's the way he put them in his book. Now, the rabbit problem. Without going into too much detail, because it's a very popular problem, he talks about how many rabbits would there be at the end of a year if you start off with a pair of rabbits at the beginning, and it takes 1 month for the pair of rabbits to become mature, and then they can have a second pair. Each pair continues to live, and each month more and more rabbits come on with this scheme. And if you look at the number of rabbits that you have each month, you have 1, 1, 2, 3, 5, 8. Well, that's neat. But if you look at it another way, you can see that the first 2 months have 1, 1 and 1. Then the second month is 2, which is the sum of 1 plus 1. The next month has 3, which is the sum of 1 plus 2. The next month has 5, which is the sum of 2 plus 3. In other words, the last 2 numbers in a sequence added together always give you the next number. And you can see here how that's generated. 1 plus 1 is 2, 1 plus 2 is 3, and then so on and so forth, and it continues forever. Now, the numbers, the first several of them, here you have them, 1, 2, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, and they go on forever, as I said. The amazing thing about these numbers is they come up everywhere, in architecture, in art, in nature. Let's take nature for a moment. A pineapple. A pineapple has bracts, and they are typically hexagonal bracts. And if you take a piece of chalk and mark one of the spirals, and then count how many spirals you have to pass to get around to the one you started, in one direction you will have 5, In the other directions, you'll have 8 and 13. Those are Fibonacci numbers. And, for example, if you go, say, to a pear tree, and you take the first branch, assuming it was not pruned at any time, until you get to the next branch facing the same direction, you're going to pass a Fibonacci number of other branches. On a pine cone, where you again have spirals, if you mark them, you'll find that the spirals, once again, give you Fibonacci numbers. In this case, this particular pine cone gives you 8 in one direction and 13 in another. Sunflower and so on and so forth. Now, there are practically endless things that you can do with the Fibonacci numbers. As a matter of fact, since 1963, there is an association called the Fibonacci Association, which publishes a journal 4 times a year, appropriately called the Fibonacci Quarterly, and they invite mathematicians and other interested parties to contribute articles that involve the Fibonacci numbers, and they seem never to run out of ideas. But let me just give you just a couple of very, very elementary illustrations. For example, supposing we take the sum of the first 4 Fibonacci numbers. That's 7. The sum of the first 5 numbers is 12. The sum of the first 6 numbers is 20. You say, well, so what? But 7 is 8 minus 1, and 8 is a Fibonacci number. 12 is 13 minus 1, which is a Fibonacci number. 21 is a Fibonacci number. So it looks as though that when we sum the Fibonacci numbers, it's always going to be 1 less than the Fibonacci number that's 2 away from the last one. And you can see the pattern continues on, so that when we take the first 10 numbers, it would be the 12th Fibonacci number minus 1. And if you want to see how this looks in symbol form, we usually use f sub n to refer to the nth Fibonacci number, and we know that a Fibonacci number is equal to the sum of its 2 predecessors, and you see here where we get f sub n is equal to f sub n plus 2 minus f sub n plus 1, and if we take and write down these each one, that the first one, second one, third one is equal to what it is by definition, and then look at the sum. So on the left side, if we take the left side of the equation and sum that, we have simply the sum of the first n Fibonacci numbers. On the right side, what we can sometimes call telescopic addition, we have the numbers dropping out. For example, the F3s drop out, the F4s drop out, the F5s. The only thing that remains when we add down is we have f sub n plus 2 minus the first one, which we didn't drop out, which was f sub 2. And f sub 2, we remember, is the second Fibonacci number, which is simply 1. So there you have the sort of a proof, if you will, why the sum of the first n Fibonacci numbers is the one that's 2 larger minus 1, 2 larger than the last one minus 1. Okay. Now, let's take a look at some of the crazy things that you can see with Fibonacci numbers. For example, we'll just take any 4 consecutive Fibonacci numbers. In this case, we took 3, 5, 8, and 13. Now, watch what happens. Suppose we take the difference of the squares of the 2 middle numbers. Well, that would be 8 squared minus 5 squared, or 39. Now, we're going to take the product of the outer 2, 3 times 13, which is also 39. And that will be true for any 4 consecutive Fibonacci numbers. If you take the 2 middle ones, take the difference of the squares, and the 2 outer ones, and we show that symbolically with the F form there, which you see on your screen. Okay, now, remember we started with 666? Well, we're going to revisit him. Obviously, as I said to you before, 666 manifests itself all over, and so does Fibonacci. So clearly there has to be a link between the two. Well, supposing we take the first, the 9th Fibonacci numbers and subtract them. Then we're going to add to that the 11th Fibonacci number and then the 15th Fibonacci number. And guess what? 666. And when you look at the subscripts, now that's the crazy part. Look at the subscripts, 1, 9, 11, and 15. And if we combine them with subtraction addition, we get 6 plus 6 plus 6, which is sort of looks like 666. Now, if you were impressed with that this will surely impress you. If we take the cubes of the first, in this case, the first, second, fourth, fifth, and sixth Fibonacci numbers, the sum of the cubes is once again 666. And not to be sidetracked by the subscripts, once again, if we take those subscripts, they become 6 plus 6 plus 6. So there's something a little strange in mathematics that we need to show some of our adults that need to be convinced about mathematics' beauty.